All right. Okay, I think we can start. I'm here today with Shunyu from Princeton, and he will talk again in our line of language models on formulating and evaluating language agents. I'm very excited, so I'll hand it over to you, Shunyu, for starting the presentation. Oh, and by the way, if there are any questions from the attendees, please put them in the Q&A tab, and then we can answer them in the end.
Cool. Can you guys see my screen? Okay. Hi, everyone. My name is Shunyu. I'm a final year PhD student from Princeton. And today I want to talk about formulating and evaluating language agents. But first, what is language agents, right? So conceptually, we all know what is a language model. And the idea of agent is one of the most ancient idea in artificial intelligence, right? You want to build intelligent systems that interact with the world. So conceptually, language agents are just autonomous systems now that use large language models to interact with the world. And to give a couple examples, this Google robot Sican, right? So it is empowered with large language model to reason about what to do in a kitchen, to satisfy a user's end, right? If the user say, I'm hungry, I just got off the running, then the robot can reason about, maybe the user needs water or energy drink, and use those large language models to reason about actions. Another very famous or cool example is generative agents from Stanford. So the idea is you have those digital agents that simulate human behavior. So each of those little agents is empowered by large language models to interact with not only the small digital town, this sandbox game, but also with other agents. And it could have interesting phenomena. For example, when one agent wants to have a party and then the information propagates through the whole town and then everybody come. So like underlying this very fancy demo is this in architecture where you have this large language model, and then you also have semantic and episodic memory, and then you have retrieval, planning, reflection, a couple of different components. So this is just obviously like two out of many papers that is going on nowadays, and this area of research is really explosive, and everybody have their own framework, have their own application, have their own domain to incorporate, large language models for their own acting kind of tasks. Obviously, this is also very hot, not only in not only research, but also industry, right? So yesterday, right? So we just finished the first OpenAI Dev Day, and we know, one of the biggest issue of language model is, ChatGPT used to be stuck at 2021, and it's really hard to update them. But if you give them access to, code or action or retrieval, then they can access up-to-date information. And apparently, this word agent is really one of the key word yesterday, and there are a lot of exciting things going on, right? So, if we think about language agents, right, we now have a lot of papers, and we have a lot of like exciting applications, like GPT plugin or the GPTs announced yesterday. We have a lot of demos and hypes, a lot of discussions, but I would argue, what we lack nowadays is systematicity, in the sense that, a lot of the projects, including some of my own, sometimes, often the reality is you are given a problem, and then you're given a language model, say GPT, right? And then you just write very ad hoc code to try to connect different components together and to work on this particular problem, right? But what we really want is a really systematic design and rigorous test, something like this, where you have a very systematic framework for how to build a problem, not only for just one problem, but for all kinds of different problems, right? You have the systematic theory, and then you have systematic design, and then you also have systematic test to make sure that those agents are actually robust. And that's one of the hardest things nowadays. So the question today for this talk is, what does it take to develop useful agents in production? And towards, actually deployable language agents, I think there are two problems that we need to study but are often overlooked. So the first question is more theoretical. It's a question of formulation. And the question here is, how can we have simple but complete abstractions and terms and concepts to capture everything that's going on for language agents, and even capture, what we want to build in the future, and how can we unify, all the different paradigms and frameworks and methodologies, and have a sense of what's going on. And here, the key insights come from cognitive science. So we use the old idea of cognitive architectures to propose a framework for language agents. The second part is more empirical. It's the question of evaluation. Here, the challenge is that, we have all those methods, but often we don't have good enough benchmarks. And by good benchmarks, I mean hard and useful tasks, but easy to evaluate. Oftentimes, evaluation is really hard because you have this very long trajectory, say on the web, or dealing with software or a robotic trajectory, but it's really hard to give a score or give a reward to such a very long trajectory. So the insights here is we can actually use real-world digital tasks, such as navigating the web or writing code to define the task. And then we can use those domain priors to design more deterministic rule-based metrics, which I'll explain later. Okay, so let's come to the first part, formulation. So, formulation is interesting because we are witnessing an explosion of concepts and tricks and ideas, right? So in the beginning, you only have large language models. Then you have, prompt engineering, which is how do you change the input of the large language model to change its output, right? And then it becomes more complicated. You have those different reasoning tricks, different ways to generate actions. You have different environments to act, right? Web, coding, grounding, and you have retrieval, obviously, to read the file. Now you have, ways to do self-reflection. You have feedback. You have planning, decision-making, memory, flow, control flow, even robotics, multi-agent. So this is very overwhelming, and the key question is, given the explosion of the problems that agents can solve and the explosion of concepts and frameworks, and given the fact that each different paper uses different terms and different concepts to describe their methods, how can we make sense of all those different agents and have a unifying kind of understanding? So this question, I would like to draw an analog to computers, in the sense that I believe we should have a system-level architecture for language agents, where language model is just a component, and analog is, we have computer architectures consisting of CPU, memory, keyboard, monitor, whatever, but CPU is only a key component. And analog, I think, is fit because both large language model and CPU are the core component of language agent and computer, respectively. However, they cannot work alone. So both are stateless in the sense that you just give language model or CPU an input, and then it will give you some result or output. But it could not handle. It could not have it does not have memory by itself, and it could not interact with the external environment by itself. And that's why you need external I/O for computers, such as keyboard, mouse, camera, monitor, and also you need internal memory, right? Register, cache, hard disk, even cloud, right? And so similarly, you need external I/O and internal memory for large language models, and that is intuition of language agents formulation. So we have this paper called Cognitive Architectures for Language Agents, and it's really using some of the oldest ideas in AI and cognitive science to try to describe language agents. So in the paper, we have like 30 pages, and we talk a lot about the history and analog and some of the conceptual arguments why we need cognitive architectures for language agents. But due to time limits, I'm going to skip them. It's really fun. You should read that. It's a history. But let's just talk about what the framework is in a very quick time. So to begin with, right? So let's first review what the formulation of RL agent is, right? And it's actually really simple, right? You have an agent, you have RL agent, you have some environment, and there's interaction, right? RL agent give the environment some actions, and then the environment give you some observation. That's it. And that's the generalist and simplest formulation of reinforcement learning. But for language agents, things are a little bit complicated, but only just a little bit. So this is our Koala framework. And to understand what it is, I think there are only 3 concepts you need to learn. And once you learn those 3 concepts, you know what's a language agent and why it's different from RL agent in some sense. So the first difference, or the first key concept is memory. Second is action or action space. The third is decision or decision making. Okay, so what is memory, right? So like I said, like large language model itself is stateless. So it is sig to sig in the sense that you give it an input, it will give you output, but it does not store anything by itself. So similar to humans, right? So we think, language agents should also have 2 types of memories. So there should be there is a short-term working memory that stores information for the current decision cycle or for the current task, right? So for example, like in your mind right now, the short-term working memory is storing things related to language agents or the talk, because that's information available or useful for the current task. But also you have long-term memory, right? So for humans, we have episodic memory to store experiences, right? So what do you do yesterday? What do you do 3 years old, etc. You have semantic memory, right? So it stores all kinds of knowledge. So for example, in your mind, hey, Imperial College is in London, which is in UK, right? That's a piece of knowledge. And you have procedure memory, right? That stores skills. And in this case, we think the weights of the large language model is kind of like an implicit kind of set of rules, and the code of the agent is in some sense a set of explicit rules for the agent. So for example, in your mind, you probably know how to go to Imperial College. That's kind of a procedure kind of knowledge. So once you have those memories, the question is, what can you do with it, right? So we know RL agent is defined with action space. And in fact, the action space is defined by the environment. So if you're Atari agent, then your action space is left, right, up, down, but you cannot define what is your action space. But in fact, an language agent can define its own action space, because it not only has external actions that interact with external environments, right, which we call grounding actions. What's different between language agent and RL agent is that because language agent also have those explicit memories, so we also have those internal actions that interact with internal memories. So if you think about like whether to read or write, and whether it's short-term or long-term memory, there are only really 3 different types of internal actions. So reasoning is to use large language model to update your working memory, right? So for example, you can ask language model a question, and then get some answer, and then you can store the answer to your short-term memory, and then you get something new, and this new information is obtained by reasoning. Obviously, you can read long-term memory, that's called retrieval, and you can write to long-term memory, and that's called learning. And notice here, how general the notation is, because for learning, right, there are many different ways to write to many different parts of the long-term memory. Right? You can write to episodic memory, semantic memory, procedure memory. You can update the ways of the language model. So it's really a simple but complete characterization of all the possible things that a language agent could do. Okay, so the last question is, now you have a space of actions. How can you actually choose which action to take, right? And this is handled by decision-making procedure, where, we split, all the actions that an agent take into cycles, where each cycle, you start with a planning stage, where you use a lot of reasoning and retrieval actions, and then you finish with the execution stage, where you have decided a learning or grounding action, which actually affects either your long-term memory or the external environment, and then you apply that, and then you get some feedback, and then the cycle starts again. So this is very similar to let's say AlphaGo. So you can imagine, in your head, you can do all sorts of different simulations about what I can do, what the opponent can do. If I take this move, I can plan ahead, whatever. But then at the end of the planning, right, you need to decide which piece to move or which piece to take, and then actually apply that to the external world, and then you get some feedback, right, which is how the opponent actually moved, and then you do it again. So the simplest way to do decision making, right, is you use language model to generate action. So there's minimum planning and it's just execution. But then you can imagine something more complicated, which is you can generate a bunch of actions, and then you can use reasoning to reason about which action is the best, and then you apply that. Even more complicated, you can reason you can generate a bunch of actions. You can simulate, what will happen in like a tree search kind of manner, multi-step forward simulation, and then choose what is best, and then apply that. So there's a lot of variance in the complexity of decision making in the Korean agents. So most agents are still very simple in terms of decision making. I think we're only starting to see more complex decision making recently, like recent 3-4 months. Okay, so there's a lot of details to be filled, and in the paper we have this very comprehensive survey that map those concepts to hundreds of different papers, and talk about how this paper has this example that fits this definition of this concept. But that's it basically. So this is a set of very simple but complete abstraction for defining language agents. But what do we want to do with it, right? So one way we can use it is to understand and unify existing agents, right? Like I said, there are like tons of papers, like tens of papers every day going on, and they all have different terms, concepts, frameworks, methods, code. But if you view them through this Koala framework, it becomes much easier to understand their structural similarities and differences, and understand the trend. So for example, if you look at this memory part, most of the agents don't have long-term memory, and it's only starting this year that we see those agents where you have procedural episodic memory. And obviously you have different sorts of grounding, but you can also see here that most of the agents is using very simple decision-making procedure where it just use the language model to generate actions. Only starting recently, right? So my work Tree of Thought is one example where you see those complicated, more deliberate decision-making where you propose, evaluate, and select in an iterative manner. So another example, right? So I talk about learning, and defining learning as writing to long-term memory is very unifying and broad and very insightful actually, because well, most of the people think of learning as just fine-tuning the language model, right? But if you think about how humans learn, that's not the only way we learn, right? So you can memorize some fact, and that could be useful for your later life, and that's also kind of learning. So another benefit through Koala framework is you can have very unifying concepts, and then immediately you can see where is the gap, because in the paper, for example, we just list all the possible learnings, and you can see a lot of work is done on fine-tuning the language model, but there are other things that are not as explored yet. So, for example, like, can the agent change its own prompt or change its own code? And that's something there's a lot of interesting things to be studied there. So immediately there are a lot of ideas for future agents if you just have this very simple and complete abstraction, and then you you cast all the work into this, and then you can immediately say where is a thing and where is everybody focusing on. Right. So obviously in the paper we discuss a lot of, I think there are 20 available paper ideas, and there are a lot of interesting discussions. But I'll just finish with another benefit that I think Koala will provide. So if you're familiar with reinforcement learning, we know it used to be a bunch of different domains, right? And each of the domain, you have your own code base, and you have your own development, and you have your own idea. And if you work on this one game, it might take you another month to set up another game, because your mindset, you're a domain expert in this game, you're not a domain expert on that game. So it's really isolated, right? But something as simple as OpenAI Gene, right, really helped develop RL agents, and really important in the history of reinforcement learning, because you have this very simple abstraction, right? What is the environment? And it's just how you reset her, how you step that, what's the action space, what's the observation space. And then OpenAI implemented a bunch of simple examples, right, for different environments. And then people can just build their own OpenAI environments. And what's good is, you have the separation of environment and agents, and now you can reuse some environment from the past, and then you can compare methods more easily, because if the agents are defined on the same environment, it's easier to compare. And really, it helps disentangle the code base, make it very structured, and make it very systematic, and make evaluation much better. So we think similarly, we can define Koala abstractions such as what's the environment, what's memory, and what's reasoning, what's retrieval, etc. And the point is, it's super simple, right? So it's just a set of minimum abstraction that takes perhaps 20 lines, and then some examples of how you actually implement that. And then you have full control how to do that. And I think that will be quite exciting for the development of future agents, where terms are unified. You can easily compare ideas or compare agents, and I think that will help develop future agents. Okay, so let's talk about the second part, which is evaluation. And this part will be more empirical. So if you think about all the agents throughout history, right, I would argue there are only 3 paradigms in terms of what kind of environment you're interacting with. So oftentimes, we have tasks that interact with the physical world, like all the robotic tasks. All the tasks that interact with humans, like dialogue. They're great because they're very practical, right? There's a lot of useful things robots or chatbots can do, but the problem here is it's really hard to be scalable, in the sense that collecting, those physical trajectories or interaction with humans is really expensive. And it's really slow. You have to wait, and it's also very hard to collect reward signal. On the other hand, what's popular in reinforcement learning so far is we can interact with digital simulations, no matter it's video games or robotic simulation or whatever. So all those different digital games, and they are great because they're scalable, right? You can train millions of steps on those in those environments, and they define reward function for you. So you can really train agents. But the problem is they're hard to be practical, in the sense that sim-to-real transfer is really hard, right? So if you train a robot in those digital simulation, it's really, really hard to transfer that into the physical world. In fact, if we can do that, then the field of robotics will be very different. That leads to this, I think, the third option, right? So We can also deal with those digital applications that are useful themselves, right? So the idea here is if you have those digital tasks that are already practical, then it's easier for them to be both scalable and practical, right? So I'm gonna talk about two examples, right? So one example is how to interact with the web, and the other example is how to interact with the code. And you can immediately see that the environment is really scalable, right? There's a lot of web data or web environments or code data or code environments in the real world, and you can use them. And it's obviously both scalable and practical. But oftentimes the problem you will see is that you need to define a good metric, you need to define a good evaluation measurement to actually measure progress and help develop agents in those domains. So in some sense, the difficulty is not the environment, but the evaluation. Okay, so let's first talk about this work called Webshop, which is done in 2021, so it's like a long time ago. But the idea is we really want to make web interaction both scalable and practical, right? So, but at that time, there has been some prior work studying web interaction, but it's hard to be both scalable and practical. So let's take a look at some examples, right? One of the earliest work that designs web interaction benchmark is for the bits. And it's like you have those cute web pages that, like you're required to click a button or type something somewhere. So it's kind of like a suite of handmade Atari games in the sense that they're small, they're reproducible, they're fake, they're synthetic, and you can solve them, but it couldn't transfer to the real world, right? Another idea is, you can try to push on the scalability, right? So the idea of this Wikinav thing is, I give you a Wikipedia page, say China, and then I give you an end page, say Imperial College London, and then I need you to click those like link in the Wikipedia page to find a path to navigate from start to end. So you can immediately say it's really a scalable thing, but it's not really that practical, and your action space is really limited to just clicking. Obviously, OpenAI has been a major player in web interaction. Even I think it's around 2019 or something, or 2020. You have something like WebGPT, where the idea is, you're given a browser, and then to answer a question, you need to really click and look into different materials, and you need to organize information together to give a comprehensive answer to a hard question, right? But then the problem often is evaluation, where it's really hard to judge whether a long answer to a hard question is good or not, right? So what you can do is you can hire humans to compare whether two answers, which is better. So that leads to this reinforcement learning from human feedback kind of idea. But the problem there is it's really expensive to hire humans, especially online. So you have to be really rich, like OpenAI, to be able to do that. It's not really possible in academia or research. Okay, so given those limitations, like we're inspired and we propose Webshop, and we can look at a demo of Webshop, right? So the idea is, you're given an instruction, right? I'm looking for a particular product, for example, X large, red color, and have some price constraint, whatever. So you have this particular requirement for a particular product, and the agent have to search different queries on this website, look at different items. They could click, items, or click, some of these buttons, to read more about the product. But the agent needs to decide for you, whether to commit to a product or go back, explore more, how to explore more, like look at more items or search again. And if you search again, what kind of queries to use to reformulate the query to make it better. Obviously, at the end of the day, after all exploration, you need to remember what's the best. You need to do some customization options. And at the end of the day, you click buy now, and you're given a reward based on how good your product is. So it's really simulating how humans shop in some sense. And the high-level idea is you have this very simple instruction following task where you give a query, you give an instruction, and then agent needs to interact with this website and then give a product, and then reward is based on the product and the instruction. But why shopping out of all the possible web, domains? So, for example, one benefit is shopping is really scalable in the sense that it provides you really rich dynamics, really scalable items, right? You have all sorts of different pages and all sorts of different buttons and elements and actions. And if you want to make this environment larger, you can collect, 1 million items, 2 million items from Amazon or all the real world shopping websites. It's also a very scalable task in the sense that you have this really well-defined problem, which is find this particular product, and you can see it's actually more possible to synthesize reward, because while it might be hard to judge, answer to a question such as, who is the best politician in America, right? That's really hard to answer, and it's really hard to evaluate the answer. Right? But if I just want to ask you, can you find me a small portable folding desk? That's very easy to evaluate, right? You can see from the image or from the text description whether it's small, whether it's portable, whether it's a folding desk, etc. Lastly, it's consisting of a lot of interesting challenges. So you have all the multimodality, you need to understand images and text and all the website dynamics. You also need to do very long horizon exploration and decision making, right? So you can imagine, we as humans will often shop for like an hour or more on those shopping websites because it's hard to shop. You have to browse through different items and you have to make a decision. That's the hardest part. So how do we build Webshop? Well, the idea is first you scrape the data, obviously, from Amazon, and so each of the product, we actually also use text mining to get a set of attributes, right? For example, for this camera, it might be LCD screen, it has memory card, it's digital, or whatever. You have those attributes, right? And then the second step, we build this synthetic website using those real data, where you have two interfaces, right? You have this browser HTML mode, but you also have this simple mode that's either for language agents to operate. And then the third part, you have human instruction, right? So what we do is, given a product and given its attributes, you can hire humans to paraphrase that to instructions. And now, obviously, it can be replaced by GPT-4. But in Webshop, that's the only part where we hire humans. Lastly, when you have a Go product, when you have like an agent product, right? You can define a rule-based metric to calculate the reward, and it's quite simple. So you just look at all the different attributes, and you just look at how many attributes did the purchase product actually satisfy. So it's just a recall in some sense, and that's it. So you can see the construction is really try to be as automatic as possible in the sense that you don't require a lot of extra human annotation, and you can scrape available items from the internet, which is vast and free and scalable. Okay, so there's a lot of experiments in our paper. I'm gonna skip all of them. Maybe just talk about two, right? So the first set of experiment is, you can build agents, you can prompt GPT-4, you can do a lot of methods on Webshop, but it turns out to be a very hard task, right? So in our paper, the best agent is around 30% like success rate, and human expert is around 60%. So why human expert is also that low? Because it's really a hard task where you need to have patience and you need to explore many different, perhaps different search queries and different products and carefully read, does this product satisfy all those features to make sure you success. Oh, by the way, success rate is really a hard metric where you have to satisfy all the different attributes in the product. So obviously that result is from 2021, 2022, but then you have a lot of GPT-4 based agents. But to my understanding, I think the best agent is still lower than or around 50%. So there's still a lot of space for improvement, which really shows, this long horizon exploration and decision making is really the hard thing to tackle in those language agents. But on the other hand, I think another good news is compared to all the RL games, robotic simulations, sim-to-real transfer is much easier. So we actually try to train agents on Webshop and then deploy them to Amazon or eBay. And here we only show Amazon, but you can see the performance is actually pretty matched, despite the search engine is different and the product distribution is different, and the website dynamics is different. This is really exciting because this means for the language agents, it's actually possible to be extensively trained on those simulated domains and then transfer to the real world, which is really exciting. Okay, so next I'm gonna talk about code interaction, right? So I think for myself, I'm very interested in web interaction and code interaction because I think those are two most useful or common modes where we as humans interact with the digital world, and they are the most general kind of interactions you can define. So code interaction, obviously, coding is a very important task. Programming is a very important task, and you have a lot of interest, obviously, of developing models and benchmark and stuff. But the problem is, most of the benchmarks today are sig-to-sig or static, in the sense that you're given a instruction and then you need to write a code in an autoregressive way, and then that's it. Then you evaluate. So that's very different from humans because we code a program in a fundamentally interactive manner, right? So it's impossible for us to just type on the keyboard autoregressively and then make it work, right? Because there could be bugs, and then you need to debug. And to debug, you might execute and see results, and then try things around, right? Or you can, write a sub-function, test that first, and then write another function, so on and so forth. Fundamentally, we code interactively and very reliant on execution feedback, right? There has been some interactive execution-based methods, but unfortunately, there's no standard benchmark for this kind of things. So the idea of Intercode is really simple, right? So we want to make coding an interactive task for language agents instead of a sig-to-sig task for language models. And the idea is you can already use some of the data from those old data sets, and you can turn them very easily into interactive games, right? Because all you need to do is provide execution feedback from programming languages, and you can turn any of the existing data sets into a interactive kind of RL environment. And you can also make new problems that is not possible before, right? So take a look at the setup, right? So Intercode is really similar to a standard RL environment, or you can say interactive agent environment, where the environment is just a Docker-based, Python, SQL, Bash, whatever program language terminals. The action is just code. So once you execute some code, you get some feedback, and the observation is just the execution result, right? So for example, in Bash, if you use this action called PWD, then you get this observation where your current folder is, right? Why do we want to do this? like first, Docker provides safety and reproducibility, but more importantly, right, you can really study new tasks that are fundamentally interactive, right? So we have in the paper a catch the flag kind of task where you have to really solve the first puzzle to know what the second part of the task is, right? So in that case, it's fundamentally interactive and it's really fun. You can unlock new evaluations, right? So previously, because we don't have those execution environments, all the batch tasks, they rely on surface form kind of matching, right? So you generate this long piece of bash command, and you have this reference piece of long bash command, and you just look at how similar they are. Obviously, it's a very, very bad way to evaluate those commands. So for us, we can just build several file systems, and then you just need to observe if the file system after the code command and after your interaction, they're the same, and that's much easier and more faithful to evaluate. But also, obviously this unlocks new methods, because for bash, you can imagine, you can, for this example task, you can write a very long bash command to make it work, but the 6-to-6 generation is super hard. But if you can have the ability or the flexibility to do this step by step, you can imagine there's a lot of different ways to do this. And so in the paper, we consider some very simple ways to design agents, right? So a singleton is just 6-to-6, right? Try again is probably the easiest agent method, right? So you execute the code. If it's not passing the example case, they just generate again, right? That's the simplest way to leverage execution interaction. So React is one of my paper, and the idea is you can use those like agents to think about what to do, and then to do so, and it could have the ability to debug or have the ability to think about how to decompose the problem, etc. So it's really leaving all the decision up to the agent. Plan and solve is slightly simpler, so you can just plan what you want to do in English, and then generate the program. And you can do so for multiple turns. So all those agents are super simple, and but there are a couple of messages from very simple methods. So first, you can see that all the multi-turn methods, they perform much better than single turn. So even something as naive as try again, the accuracy is much better, because you can take into account what is your failed program, what is a failed example, and then you can try again. That makes things better. You can incorporate those kind of feedback. But obviously now, different methods are best across different tasks, which is interesting. But you can see, even those very classical tasks, so spiders and NLP, they're defined like, I don't know, like 5-6 years ago. We're still far from solving those simple problems, right? There's huge room for improvement, and it's really exciting to keep pushing on all sorts of Intercode tasks. And what's also exciting is, Intercode is more like a gym environment, right? So it's not just one task, it's not just one benchmark, it's just not, you can turn any task into Intercode, right? So you can have a suite of different tasks inside Intercode, and it's really easy to adapt your own task into Intercode environment, and you can try to deploy agent across those different domains, which is really exciting. Okay, so lastly, I want to briefly talk about this really new work that we just released last month. So it's called Swe-bench, and the idea is, so far, all the problems like people have tried before are simple in the sense that you are given one line of instruction. For example, like, can you sort this list? And you write like 5, 10, maybe 20 lines of code to solve it. But that's really more like code interviews, that's more like LeetCode, right? But real world programming is not LeetCode. It's not that simple, right? So we're really trying to push the complexity of programming and then provide this really hard benchmark, but incredibly valuable. So the idea is you're given a GitHub issue, and you're given a repo, and then the language model is tasked with generating a PR, generating file diffs to actually solve the issue. So the idea is, the input to language model is something like this, right? So you have this repo, and you're given all the files, right? You can imagine there's like millions of tokens in this repo, and there's this description of what the problem is. And on GitHub, you have those pull requests that have high quality patches that solve the issue, right, with a file diff, and they often have unit tests. So what we do is we just collect those issues and we collect those pull requests and we collect those unit tests. And language model needs to write a file diff, and then what we do is we just apply the file diff to the repo and run the test, and it's very easy to evaluate, success or not. But it's obviously a very hard task, and if you do this with seq-to-seq, language model can only solve at most 5% of cases, even with oracle retrieval, in the sense that input context is really huge and it's impossible to fit all the files into the input of the language model. So you can use some retrieval to select some of the files into the repo. But even if you know what the ground truth pull request changes, what files it actually changes, it's still a very hard task. And obviously, this is a very hard and very practical task that requires interaction and agent methods. And there's lots of to-dos, and we're excited to explore all the different methodologies that's possible to really develop useful coding agents that are not just solving, lead code simple kind of tasks, but solving, real-world tasks that have useful values, right? How to actually debug a repo. Okay, so a quick reflection here will be, what is the takeaway for this evaluation issue, right? How can we have cheap, fast, yet high-quality evaluation? And I think the point I want to make from these two examples is, oftentimes we're relying on human evaluation or language model evaluation, right? So they have their complementary pros and cons, right? Human eval is high quality, especially if you're rich, but it's not really scalable because it's really expensive and it's really slow to collect those human evaluations. It's really hard to do that online. So most people do this offline. You can use GPT-4 to evaluate GPT-4. It's really scalable, though it costs money, but it's really not there yet in the sense that those language models are not trained for evaluation yet, and oftentimes you have hallucination, and it just doesn't work yet. But the examples I show is where if you really have a domain and you have the domain priors, you can really, based on domain knowledge, define a rule-based kind of deterministic evaluation that is high quality and scalable, unlimited, free, and fast. You just need to understand the domain and define that. Okay, to summarize the talk, language agents are a new kind of agents that rely on large language model and reasoning. It's really exciting. We have a lot of ideas and hypes and applications and stuff, but two things we lack: series and benchmarks. To formulate language agents, we can use classical insights from AI and Coxsci, and to evaluate language agents, we can use real-world digital tasks, and we can define good metrics. And I think there are also two domains or two parts where academia would uniquely help, right? Because companies like OpenAI or Google, they have resources, they have compute, but as academia, we have more access to those classical or interdisciplinary ideas, where you can use those ideas to build concepts, to build benchmarks, to build frameworks. And also in NLP, we have those tradition of building good metrics and good tasks. You really need rigorous kind of testing, and I think those two parts, obviously academia could help much more than what I talk about today. So I really encourage you guys to check out the Koala paper, and in section 6, we list out a bunch of future directions for language agents. Obviously, you can email me or talk to me, ask questions here, or use the website to give me feedback. I'll finish here, and thank you guys.
Thank you. Okay, muted. Are there any questions in the Q&A?
Ask questions here, or use the website to give me feedback. I'll finish here, and thank you guys.
Okay, so far there are no questions in the Q&A chat. I do have questions. The first thing I wanted to ask is, what do you think makes these things work? So like, what is it, for example, in the trained data set that these models have been trained on that does allow them to kind of reason and act in this way? Because they haven't been explicitly trained to do this as an objective, right? So then what is it still that makes it possible?
Yeah, that's a really great question. And I think the answer is, so far, those language agents are not, I think they're not particularly trained for those agent tasks, right? But you can imagine there's a lot of internet data that have similar kind of common sense knowledge. For example, WikiHow, right? Those data tells you, if you're given a task, how can you plan, or how can you have some procedure. And you can imagine for something like coding, right? You have those trained data from GitHub that tells you how to issue a code as action in some sense. But I think you're right. Even like models like GPT-4, they're not like designed for agent-based models. So that's why we now need a lot of code wrapped around GPT-4 to decompose those actions or reasoning or planning or decision making into parts, and each part hopefully you can have some good reasoning ability to make that work. I think another exciting future direction that I haven't covered in the talk is, like my talk is like, how can I go from language models to language agents? But I think now we can also think about how to go from language agents to language models, right? So in the sense that, when we scale up those language models, we don't know how they're going to be used, right? But now we have explored all the different use cases. Perhaps we can turn those like trajectories back into the base model. If we have a better sense of how they're going to be used, maybe we can train a more suited base model for agents or whatever. And one of my work is called FireAct, and it's trying to explore this idea. And you can fine tune those language models on those trajectories of agents, and that just perform much better. And it's really a cheap way to increase the performance of those agents.
Yeah, that makes sense. So I was just looking at this FireAct paper indeed, but do you then think that purely fine-tuning is somehow enough, or should we also be modifying like the structure of the, I mean, we do these autoregressive models where we kind of see, okay, these words are likely to be together, these words are less likely to be together. Do we need to modify something also in the structure of how we represent the data, or is indeed fine-tuning on like a wide space of like action, data action somehow enough?
Yeah, so that's again a really good question. It's like you're asking whether fine-tuning or just adding more data is enough, or to better enable those agents, do we need to change the autoregressive nature of those language models as next token prediction questions? So I don't know. I mean, that's a great open question. I think we should explore the limit of fine-tuning first. Like we haven't, I think there is seriously understudied. But I do think there are some fundamental limitations of next token prediction, in the sense that they're kind of myopic, right? They're just token by token. So my paper Tree of Thought is actually motivated by this. I think there are some interesting ideas to explore around, changing the objective or changing the architecture of the transformer to make it better suited for agent tasks. But I also think, in the short future, we should explore more fine-tuning, because I think that's seriously understudied. Yeah.
Yeah, I think that makes sense. No, I think I really like this idea that first, indeed, let's explore how far we can get things with purely fine-tuning it on certain specific data sets. And then once we know the limits, then we can also more properly define what are the changes that we need to make in the autoregressive nature of these models to then make certain things work. This is not a question, but a comment. One project that we're working on also in these kind of generative models is how do they actually combine information from their trained data set. So if we have a certain pattern in the if we observe a certain pattern in the output, does that mean that it has to have been seen also in the trained data set, or do they somehow creatively indeed combine different patterns to then generate outputs? And I think in terms of robots, actions, these kind of things, you could also define these kind of patterns very nicely somehow thinking, okay, if you have this fine-tuning data set, what has been shown to create this data set in your trained data set? Are then all these events also able to be generated in the test? Are there more events being able to be, more actions, I should say, generated in the on the test set? But yeah, all of this is very cool. Are there questions from the room? No. Okay, I think also from the chat, we currently don't have any questions, but this might be because the chat is not working, because in the beginning we weren't sure if it is. So it's not, your presentation was great. I think then we can end it here. Thank you so much. I thought it's really, really, really cool work. And yeah, that's it.
Thanks for inviting me. All right, thanks.
All right.